Hello dear students, welcome to second lecture of elasticity. In this lecture, we'll discuss about strain. So let us get started. Consider a body, suppose it has a length L. It has a length L, that is this part of the length L. And suppose we try to pull the body from one side and this side is fixed. Just imagine this part is fixed. So this is the wire and this is the same wire. I have just drawn it again. Okay. If I pull it, obviously it will stretch and its length will increase by how much amount? Delta L. So the change in length is delta L, or we can say the increase in length is delta L. This triangle represents delta. Okay, delta means change. Delta means change. So we can say strain is change in dimension per unit original dimension. So what is the change in length? Delta L. What is the original length? L. Therefore, the strain of a linear body is given by delta L by L. So now we have a very brief idea about what strain is. Strain is basically change in original dimension divided by the original dimension. And here the dimension was what? Length. Why length? Because the body is a linear body. So length is the prominent factor here. Now let's discuss volumetric strain. Volumetric strain, as it shows, change in volume per unit original volume. Now suppose we have a balloon and we due to some mechanism we press it from all the sides. Suppose we press it from all the sides like this, and so that the body gets compressed. Initial volume was what? V. Initial volume was V, and after compression the new volume becomes V minus delta V. The final volume becomes what? V minus delta V. Can I say that the volume has reduced by how much amount? Delta V. Or I can say delta V is this part. That's pretty obvious. Delta V is this part. Therefore, the volumetric strain, this was longitudinal strain. Volumetric strain is given by change in volume per unit original volume, because we have change in dimension per unit original dimension. What is the change in volume? V final minus V initial by V initial. What is final volume? V minus delta V minus V by V. V gets cancelled, minus delta V by V. Now what does this minus indicate? Obviously we knew that the volumetric strain will be change in volume per unit original volume. But what does this minus indicate? This minus indicates that the dimension of body has reduced. In this case, the dimension is increased, that is the final length is increased. Therefore, the strain was coming out to be positive. But in this case, the final volume has reduced. Therefore, the strain will be coming out to be negative. So, if the strain is positive, the body has grown, or we can say enlarged. But if the body has a negative strain, it means the size of the body has reduced. Okay. Now let's come back to shear strain. Remember the experiment I showed you with that book? Let me show it again so that you people can kind of get familiar with what I'm discussing. This is the book. I put my hand here and apply a force, and you can see the top surface moving relative with the bottom surface. This is the top surface, this is the bottom surface. There is a relative movement between top surface and bottom surface. See, some angular movement has been created. So this is called shear strain. Sorry, that was shear stress I discussed in last class, and in this class I will discuss shear strain. Now suppose when I apply a force in the topmost surface, the body, I apply a force in the topmost surface, the body moves by an angle, a very small angle theta. Therefore, the shear strain will be equal to theta, but in radian. I hope you know what radian is. Okay, the unit of angle will be radian here. Suppose the displacement is delta x and the height is h. Can I say angle? We all know what is angle. Angle is arc upon radius. So what is the arc here? Delta x. What is the radius here? H. In general books it is given as simply x, and it's a very small deviation, so x is very small. So x upon h is given by your shear strain. Now, one more thing. Shear strain, any kind of strain. Suppose we have discussed strain here. So strain is basically what? Either it is change in length per unit original length, or change in volume per unit original volume, or length upon length. So in every case we know that it is dimensionless. Why dimensionless? Because the numerator and denominator have same quantity, so the net dimension will be nothing, in short, slash unitless. It is also unitless, there is no particular unit. Okay, now one more thing I'd like to say, this, remember stress was what? Restoring force per unit area. Now what is the unit of restoring force? Newton per meter square, that is Pascal, we all know it. Newton per meter square is Pascal, you have studied this in class 9. Therefore, and its dimension will be, I hope you can calculate it, MLT minus 2, ML1 minus 2. Okay, so that is the dimension of this stress. Okay, this is strain, and the second quantity is stress. Kindly note everything down. So students, our next topic is Hooke's law. It's a very important topic when we talk about any kind of exam, or maybe this chapter also. It's one of the most important topics, the Hooke's law. So what exactly is Hooke's law? It's again very simple law. It's not that difficult. It says for small deformation, stress developed in a body is directly proportional to strain. Now before analyzing this, let's go through what is stress again. Stress is restoring force developed per unit area. Now again I have said, if you apply more force on a body, the stress developed will be more. Simple, fair enough, right? So you can simply say the stress is a measure of how much force we are applying. Fine. Now I'll discuss this again. What was stress? Restoring force per unit area. Suppose I have this body and I've pulled it with some sort of force F. So higher the force I apply, higher will be the restoring force. Higher the force I apply, higher will be the restoring force, and higher will be the stress. So in simple words, I can say if I apply more force, then stress will be more. So whenever I talk about stress, just think that how much force am I applying. So stress is proportional to what? Force applied. Okay. Next is, what is the strain? Strain, in simple words, is change in length per unit original length, or change in volume per unit original volume. In simple word, it is dependent upon change in dimension. And when the change in dimension will be higher? When body is deformed more. Suppose a body is deformed by a very small amount, so change in length will be very small. But if a body is deformed by a very large amount, the change in length or change in dimension will be higher. So in simple terms, higher the deformation, higher the strain. So sorry, I will written stress here. So strain is proportional to deformation. So just keep these two things in mind, and it will be very easy for you to understand the topics from here. Stress is proportional to how much force you are applying, and strain is how much deformation it is producing. Now think about the body. Higher the force you apply, higher will be the deformation, right? And that is what Hooke's law is. Higher the force, higher the deformation. Higher the stress, higher the strain. Stress is directly proportional to strain. Fair enough. I hope you have understood this point. So if proportionality constant comes, which is equal to capital E, okay? So capital E is equal to stress upon strain. Capital E is also called modulus of elasticity. Capital E, or the modulus of elasticity, is the ratio of stress upon strain. Now, let me give you one example. Suppose you have a copper rod and an iron rod, okay? Two exactly similar, everything, their length, their area of cross section, everything is same. Now you apply a stress of suppose F here, and you apply the same force F. I'm talking about force again, or you can say we are applying the same stress in these two. Will the strain developed be same? Or okay, let's not take copper and iron. Let's take a more easy example. Instead of iron, consider it to be rubber. Okay, consider it to be rubber. Having same dimension as that of copper, that is the area of cross section, the length, everything is same as compared to copper. Now we are applying same external force here. Now think about it, whether the strain or the deformation developed in both the bodies same or different. It will be different, and you can understand it will be higher in case of rubber, because the rubber deforms even when we apply a small amount of force. But in order to deform copper, you need a higher amount of force. So in this case, obviously, rubber will be deformed much, like the deformation in rubber will be higher. So in this case, we can say that the ratio of stress upon strain depends upon the material. It depends upon the material. Understood? So, because every material will experience different amount of strain, or we can say every material will experience different amount of deformation whenever a particular force is applied. Right? So the ratio of stress upon strain, or we can say the external force upon whatever the deformation is produced, it will depend upon the material of the body, because it varies from material to material. So it is a property of material of the body. The modulus of elasticity, it depends on the material of the body. I hope this part is clear. The next is types of modulus of elasticity. How many types that we have? Depending upon the types of bodies, we have basically 3 types of modulus of elasticity. We'll start with the first one, that is Young's modulus. It is for linear body. It's a very important point, linear body. Linear body means those bodies whose length is prominent. So we have a body of length L having area of cross section A. I hope you understand what area of cross section is. Area of cross section is A. Now when I pull it with some external force, obviously its length will extend by how much amount? Delta L. And there will be a restoring force developed in this. Alright? A restoring force will be developed in this. So, Young's modulus, since it is defined for linear bodies, so in linear bodies, what kind of stress is developed? Normal stress. Kindly go through the previous video. I've discussed there. In linear bodies, the stress is normal. Why normal? Normal means force is perpendicular to the area. The force is perpendicular to the area here. So the area is like this, and force is like this, and restoring force is like this. So normal stress is developed in linear bodies. And what kind of strain is developed? A longitudinal strain, or we can say the strain along length. So F by A upon delta L by L, stress by strain. So FL by A delta L is equal to Young's modulus of the body. I hope this part is clear. Kindly note this down. Next type of modulus of elasticity is bulk modulus and modulus of rigidity. This is the third part. So we'll first go through bulk modulus. So what exactly is bulk modulus? The bulk modulus, as sounds, it is related with bulk bodies, that is the bodies having volume. So in this case, suppose we take a balloon or any 3D body and we compress it from all the sides by applying some sort of force F. Alright? So we know first of all that the volumetric strain is delta V by B. So in order to compress it, the force has to act perpendicular to the surface. Therefore, the stress developed will be normal stress. Okay. Therefore, bulk modulus denoted by beta is equal to normal stress upon volumetric strain. Alright, it is for 3D bodies, or you can simply write bulk bodies. Okay. Now, first of all, what is normal stress? The force applied per unit area. Now, it's important to understand that normal stress is restoring force per unit area. Here, external force is being applied, and this is what? Restoring force. And we know in equilibrium, F external is equal to F restoring. So, in case of F restoring, we can simply write F external per unit area by minus delta V by B. Now, what is external force per unit area? External force divided by total area is the pressure. I hope you all know what pressure is. Pressure is force per unit area, where the force acts perpendicular to the surface. So this force is acting perpendicular to the surface. All these forces are acting perpendicular to the surface. So external force divided by total area will give us pressure applied by minus delta V by V, or in simple term it can be written as PV by minus PV by delta V. I hope this part is clear. All right. Next is since P is the net pressure, I'll just write it here. Net pressure. Next is your modulus of rigidity. Modulus of rigidity means shear stress upon shear strain. It is applicable in these kind of body, as I've shown previously shown with the book. So the shear stress is how much? F by A. Strain is theta, or we can also write it as X upon H. So it will be F by A upon X upon H. It will be FH by AX, represented by eta. It is called as ETA, eta. Okay. Now one more thing. This P is the pressure across the outward surface and inward surface, or in simple terms, it is the difference of pressure. The outside pressure minus inside pressure, that is the net pressure. So in some book, it is also written as delta P. You can also use delta P here. So it will be minus V delta P by delta V. With this, I would like to wind up today's session, and we'll start solving some questions in the next class and go through the other topics. Okay. Thank you.